Okay, so that's first of all, my name is Antti Pirinen. I'm working at Helsinki Institute of Physics. I've been working about 1.5 years at CERN. I was doing my master thesis there. The topic was intrusion detection in grids. So the same thing what the Luottokunta is doing. So they're checking that nobody is using your credit card. Well, nobody shouldn't use your credit card, not even your wife or men. So I was doing the same thing for the distributed computing. And today this topic, petascale computing, so, well, today it's petascale, what we are talking tomorrow, we put 1 0 behind it and the things go and go and go to greater and greater amounts. First of all, so LHC is back. So it means that we didn't have black holes, at least yet, and we have had and we have had already the first collisions at the detector. And some background about from HIP. So we are coordinating Finnish research at CERN, because otherwise all of these universities that we see here, at least, so they're doing something physics-related research, and if they would operate directly with CERN, they would need 5 different secretaries there to guide the physicists to correct place, and so on. So in that case, we are able to have more people together, and it's easier to do things when you have a bit bigger mass. And okay, we have about 120 researchers and 5 research programs, so on. Well, this is the bit more interesting part. So what is CERN? I think quite many of you have heard about it. Some of you might read the book Angels and Demons, where we know these great red brick buildings at CERN. I didn't see any of those, but it doesn't mean that there couldn't be somewhere at the area. But we could say that it is one of the biggest oven in the world, where you could put a lot of talented people together. You gave them, or you give them some amount of money, and you give them a task to do something that can be solved today. And the current, well, this LHC accelerator should be the most powerful instrument on the planet when it is fully operating. And it is underground. We should find the answer if the Higgs boson exists. I like this slide because every year, okay, I just update this number here. Last time it was 2009, today it's 2010, next year is 2011, and so on. So there should be some kind of script that updates this year +1 system. But however, and the Large Hadron Collider, so it has this 4 experiments. The point of having multiple experiments is not to spend a lot of money, but we have to have 2 different setups. So if the other one detects something, the other one has to detect the same thing also. Because if we are using the same kind of system at the both places, it's possible that we have a common mistake in design, and we can't trust the results. For you who like numbers, here you have some small print. Okay, it's almost 27 kilometers long. We have about, well, almost 10,000 magnets, 2,808 proton beams, blah, blah, blah. I'm interested about this last number here. So we have 600 million collisions in seconds. So that's, in that case, it comes to my world when I'm thinking this in IT point of view. And the people who don't know physics, this image explains what it's all about. You take two bunches of protons, you collide them, and you take a look what comes out from the detector. It is so trivial, as could say. So in principle, this is not any rocket science in some way. Some other might have a different opinion about this one, but and okay, so what makes this challenge big is that when we have this 6 million collisions a second, each collision is about 1 megabyte. So there you can calculate how much data is coming out from the detectors. Unfortunately, we are not able to store all of these, so we have to throw plenty of data away and just hope that the things that we were looking for were not in that set of data. And here the middle picture is what we see in detector. And this picture on the right-hand side of the slide, this is what we are looking for. If Higgs boson has a fixed energy. Well, the problem is we don't know if it has, so it might be this kind of, or physicists calculate the other model that it could be. So it means that from this middle picture over there, we are looking plenty of this right-hand side kind of images. And this makes this challenge so huge that we have plenty of data, we don't know what we are looking for, but we still have to prove that something exists.
Can you take Higgs boson in 2 minutes?
In principle, yes. So now I have to read from the paper because I was calculating that if everything goes well, so you should see 1 Higgs boson once a minute, if you know what you're looking for. If you don't know, it takes a bit longer. But in principle, yes.
But I meant an explanation on what it is.
Ah,
so would it take?
Sorry.
I know that I've heard a 2-day presentation from it, but we don't have all that time now.
Well, in short, Higgs boson explains why things have mass. It should explain why these drops, why we have force between these two things. So why the weight, why you see the numbers when you're standing and when you are measuring how much you weigh. So in short, what is the reason of mass? Probably. Okay, and about this data handling, so 15 petabytes, it's pretty much data for us. And it has to be stored, it has to be analyzed, there has to be a way to access it from all around world in a secure way. So if we would be one company, it would be easy, because then we could say we are using this solution, period. However, because now we have plenty of different institutes, different cultures, and well, different culture is the biggest, biggest issue. So now we have to discuss with people what are the ways that we are working together to solve this problem. And now we come to this topic of the presentation. So there's 2 ways to do petascale computing. Either you are rich, or you have rich uncle, or you have a rich sponsor, and you just buy a computer, as this Jaguar over here. So that's the easy way. Or you are the poor, as we are. It means that we are looking for a lot of other cores, and we are collecting our resources together and see if we get something out from that.